Hello and welcome to this clip going through question 8 from the end of module 2 practice questions in the textbook, page 88 to 89. If there's any mole calculations that come up, I'll try and use the DMEMA technique, data moles, equation moles, answer. I have a separate clip on this particular technique which you can look at on my channel. It's just called DMEMA technique for mole calculations, I think. So let's get started. The first question asks you to state the full electron configuration of phosphorus showing subshells for 1 mark. And I'm just writing a few bits and pieces on the answers to help sort of explain what I'm writing. Phosphorus has 15 protons, and there must be 15 electrons present. So if we take that arrangement, we make sure that the superscript numbers add up to 15. 2 plus 2 is 4 plus 6 is 10, plus 2 plus 3 plus 15. So in the next part, they want you to write a balanced equation for the reaction, and they've described the reaction so you can construct a word equation from the information. So starting with the reactants going to products, look at what it says. Phosphoric acid can be made as the only product. So that must mean phosphoric acid is on the right-hand side. So phosphorus oxide and water go together to make that, because that's what the question tells us. So now we can put in the formulae. So my advice would be to leave spaces for the balancing numbers. So because I know that I've got 4 phosphoruses on the left-hand side, and I have H3PO4 on the right, which has 1 phosphorus in it, that becomes a 4. And now because I have 12 hydrogens on the right-hand side and 2 on the left, I need 6 oxygens. Sorry, 6 waters, I should say. Okay, so now we can go on to the next part. So, in this one, they're asking for the oxidation number of phosphorus. So, if you use the oxidation number rules, you can put in +1 for hydrogen and -2 for oxygen. So what you've got to remember with oxidation numbers is you assign them according to each individual atom. So each individual hydrogen is +1. Each individual oxygen is -2. But the oxidation number of the whole species, the H3PO4, has to be 0. So now we need to multiply the individual oxidation numbers up to see what effect they have on that overall charge or not, as the case may be. Okay, so this is a +3 from all 3 hydrogen atoms and -8 from 4 oxygens. These +3s and -8s are not oxidation numbers. The oxidation numbers are in blue. The numbers in black are simply how many times the oxidation number has been multiplied up. So therefore we can say that the oxidation number of the phosphorus must be +5, because +3 + 5 -8 equals 0. So now we can state in our answer that the oxidation state of phosphorus is +5. So I'm moving on to part C. I just realised the way I've printed out the first bit, the student measured out 150 centimetres cubed of 0.960 moles per decimeter to the -3. I haven't used the right subscripts or superscripts, so I'm going to change that slightly. So to organise my answer, what I do is I put data moles, equation moles, answer, and I put the species across the top, and in each of the little cells where data and NaOH match up, for example, I could put something in there. So the data that we have is 150 centimetres cubed, which is 0.960 moles per decimeter to -3. So by doing n equals c times v, you've got 0.960 times 150 over 1,000. That ends up, if I put it into my calculator, as 0.144. So we can put that in as the answer to part I. Then it says calculate the minimum volume of 0.500 mole per decimeter to the minus 3 H3PO4 that the student needs to add to completely react with the NaOH. So what we've got to do is look at the mole ratios. So we divide the number of moles of NaOH by 3 to get the number of moles of H3PO4 using the 3 to 1 mole ratio in the equation. That's our first mark. It's a 2-mark question, so the second mark is to work out the volume. So that gives us 0.096 decimeters cubed. You could also, if you wanted, put 96 centimeters cubed, but make sure the units match the number. So the next question, sorry, that should have said part I. When they mean a pure sample, they mean just the ionic salt. Obviously, sodium phosphate is an ionic salt. You can see this because it's been made from the reaction of an acid and a base. In other words, the sodium has replaced the hydrogens in phosphoric acid to make sodium phosphate. If you have a solution of sodium phosphate, that's not necessarily a pure sample because the water it's dissolved in would be another substance. So in order to get the mark for this, you need to say how you get rid of the water. So you'd need to evaporate the water to leave the salt behind. So when it says what's the maximum mass of Na3PO4 that the student can obtain from this experiment, quote unquote, means using the quantities provided. So looking at the equation, we can also see that the number of moles of Na3PO4 is also 0.048. So we know that the mass is going to be moles times molar mass. So we can take 0.048 times 164.0 to get 7.872 grams. So now we can go down to the final part. So all they want here is the formulae of the two ions that calcium phosphate is made of. That shouldn't be too difficult to not only work out what calcium phosphate breaks up into, but also to construct the charge for the phosphate ion. Okay, so that takes us to the end of question 8. Hopefully it's been a reasonably useful walk through what to do and how to think your way through these types of questions. So, as always, thanks for listening, and until next time, see you soon.